So how to get rich without the axiom of choice? Because it's known how to do it with, so let's do it. Alright, so I should start by saying what the axiom of choice is. So the axiom of choice tells you that if you're given any collection of non-empty sets, so let's say AI, I, and I, well, you can choose an element from each of them. So there is a sleek way to say that, which is that the Cartesian product is non-empty, or you can say it more transparently. There is a function f from I to the union such that f of I is in AI for every I. So, equivalently, so that's kind of a shocking statement of the axiom of choice. The Cartesian product is non-empty. So this seems like, especially this last statement seems very reasonable, but historically this has been a controversial axiom because it has led to the discovery of many weird objects. So for example, there is the existence of non-measurable sets. So I won't say exactly what this means, but it's some pathological subsets of the real that you cannot really measure. You cannot really say what dimension they have. And even worse than that, there is something called the Banach-Tarski paradox that I mentioned in my abstract. So let me state it. Given B1, the unit bulk, so it's just a subset of R3, we all know. Then you can decompose B1 into finitely many pieces, move and rotate these pieces around and get two balls of the same dimension. So there are S1 to Sn, and n can be taken very small, I think maybe 7 suffices, I don't remember, but at least 30 or something like this suffices. Decomposition, I should say, such that the pairwise disjoint and their union is the ball. But they can be translated and rotated to S1 bar, S10 bar, such that you take S1 bar, take the union, this one again. This is the unit ball plus one more unit ball. So let's say translate by just translate this ball by 2 units. So you get free matter for nothing, right? You get a ball, slice it into pieces, you rearrange the pieces, and you get 2 balls. That contradicts everything we know about conservation of matter, energy, everything. Of course, you know that you need AC for that, because those sets will end up being very weird, non-measurable in particular. But this gives you a very nice way to get rich, because
the richness is non-measurable.
I guess not. I guess it doesn't quite work, but you get rich still. So, you get rich
No.
in a theorem. In theorem, you can get rich. It's up to you to apply that. It's up to the engineers. So you can get rich because you can take a bowl of gold and use this, just with some work, I guess, but it's not too much. Use this to get two bowls, sell them back, or get even more bowls, sell them back. Just get free matter. So from free matter, you get lots of money. But okay, I mean, so far nobody has managed to apply this in real life, apparently. So maybe this means that the axiom of choice is false. Oh, I will also mention one thing. Well, Kevin mentioned in his email that it was not only about getting rich, but there was also math could also give you power and knowledge. So I want to say AC also implies that you can have power and knowledge. Implies you can predict the future. So I'm not gonna give a talk about this. I gave a talk about this 2 years ago, but I will just write the statement because I think it's an interesting statement and it's pretty cool too. So that's a paper by Hardin and Taylor if you want to look it up. If you go on my webpage, I have a talks subpage with a list of reference for this talk, so we can access this here. So in what sense can you predict the future? So as you can imagine, it's some very convoluted sense, right? But still you can do it. So theorem. So given a finite set of states, S. So this you can think of as representing the state of the world in a particular time. And you're going to look at the function from the real to S. And that's going to kind of tell you the state of the world at a particular time. So each function gives you the state of the world. So each function kind of gives you, tells you everything you ever need to know about the future, the past, and the present. So what I want to say is there is a strategy, I'll call it sigma, taking as input f, which is a function not from the reals to S, but from the past to S. So from some initial segment of the reals to S. So that's the past. So I will feed this strategy the past. I know the states of the past, let's assume that. And the strategy will output me the future. So it outputs f bar, that's a function now from the reals to S, such that if you restrict it to the initial interval, this is f. And this strategy has the following property. So you know this strategy you can compute without any information. I mean, you use the axiom of choice because you select something in very clever ways, but you don't need to know the state of the world to compute the strategy. I mean, you need to know the past state, but not the future. But then, for any function g from the real to S, so this would be true states of the world. So that's what you want to predict as the real thing. For any g, if you look at g, you look at the set of times so that your prediction will be correct. So you take past, you apply the strategy to it, and then, okay, you just want it to be correct to some extent, after some epsilon. You cannot really predict the future in a very long time interval, just a few seconds from the current time. So if you feed your strategy the past, you get the prediction, and it succeeds if it's equal to this. So the statement is this set has measure 1. I'll go over the statement because it has many information. I guess not measure 1, full measure. So what this says is I have my strategy, and if I look at the set of times so that it works, so that whenever I feed the strategy the past, I get the future at some small interval, then this set of time is correct. So the strategy is almost always correct. So in that sense, you can predict the future using the axiom of choice. So just saying, the axiom of choice is very powerful, gives you knowledge, power, and money. But again, nobody has managed, apparently, to predict the future using this so far. So maybe the axiom of choice is false. After all, I mean, we haven't observed a non-measurable set yet in the wild. So today I will assume that the axiom of choice is false. And actually, I'm going to assume that all sets are measurable. And I should say there is a result of Solovay that says that it's possible, so it's consistent. If AC fails, that all sets are measurable. Plus, we still have a lot of the axiom of choice that's left. We can still choose from small functions from natural numbers or somewhere, for example. This is consistent with enough choice to develop basic analysis. So you can still do something, even though you don't have the full axiom of choice. So this is a weak choice principle called DC, but I don't want to go into the details. So it's not completely ridiculous to assume all sets are measurable, because you cannot disprove that. You cannot prove that this is false. And as I said, in the wild, we haven't seen a non-measurable sets. So I will assume this, and I want to get rich still, right? So let's not forget where we are going. And so I will prove the following. There is an equivalence relation E on the real numbers, such that if you look at the size of the equivalence classes, this is strictly bigger than the number of real numbers. So you can ask what this means exactly in that case, because you have a certain choice, so what are coordinates exactly. So this means there is an injection from the reals to the equivalence classes, but not vice versa. So there's no injection from R mod E to R. And, well, that should strike you as very weird, because, I don't know, let's try to think of a picture of that. Lots and lots of real numbers, which you can still, I guess, think of them as dots. Then, the equivalence relation induces a partition. So here are the equivalence classes. And then what this says is that there are more boxes than points in the boxes. So, well, it looks a bit ridiculous, but nevertheless, the theorem. So I took this proof from, I mean, it's really a proof from descriptive set theory. It dates back from the theory of Borel equivalence relations, and I won't say too much about this. But I took the proof from a talk by Michael, Ray, and Lieber that you can find online, and there is a reference on my website. And he calls this how to get more things by forgetting where you put them. So that's also a nice catchphrase. And if you think about it, that's exactly what's going on, because you're forgetting some of the structure. You just know you have boxes now. You don't have points anymore, but you have more boxes somehow. Yes.
So does the arithmetic of cardinality change in this setting?
Yeah, so that's a good question. So if you don't have choice, yes, you have. So we know that with choice, cardinal arithmetic is very nice with infinite cardinals. So for example, mu times lambda is the maximum of mu and lambda for infinite cardinals. But for when you don't have the axiom of choice, it's no longer true. So this becomes a mess. And actually, it's consistent with failure of the axiom of choice that, let's see, the real is a countable union of countable sets. But it doesn't mean that it's countable. So there are some weird things going on. So lots of weird things going on with cardinals. That's why I was very careful about saying what is meant by cardinals. In general, actually, usually we define cardinals in terms of types of well ordering. So you assume that every set can be well ordered. But it's equivalent to the axiom of choice. So sometimes sets don't even have cardinals, but you can still define them relatively to each other using injections. So this is what's going on here. So yeah, that's it.
So yeah, so the real is a countable union of countable. Then without axiom of choice, you can get poor.
Yeah, that's true. Although in that case, it's not true that the reals are countable. I'm assuming more. I'm assuming both sets are measurable plus this DC principle actually. So it's not good. It works more or less well for the reals. Beyond the reals, for very wide sets that you don't really have any use for, yeah, cardinality gets messy. But once everything, yeah.
I'm guessing that, so you're saying that there is no injection from R mod E to R.
Yeah.
I'm supposing there is also no surjection from R mod E to R.
I don't know. I hope so. I will try to see about that. I haven't thought about it too much.
But the cardinality relation is defined purely in terms of injections, is that right?
Yeah.
Okay.
Well, I'm not defining it. I'm just saying that particular
Okay.
case.
Okay. Okay. I will leave it.
I think it depends on the uses you're making of it. I'm not an expert in that.
Okay, fair enough.
Well, because you certainly have a surjection from R to R mod E.
Yeah.
Just put it in the boxes.
Yeah.
Yeah. Right. I mean, you can get one way. I think some of these directions about injections implying surjection the other way, or surjection implying injections, they go through without the axiom of choice, but one of them doesn't. So I don't remember which does. So it's all very, everything that was trivial with choice becomes hard. So I'm not an expert in that. Sometimes you can do some things, but it's much harder. So this is an example of that. I should just say you can ask, can't we build an injection? So let's try to build an injection from. So assuming choice, we can build an injection. So assuming choice, this is not true, of course, because we can build an injection from R mod E to R. How assuming choice, for any class in R mod E, you can use AC to pick f of C in C. So you can use the axiom of choice if you have all those classes to pick an element from each. So the axiom of choice tells you exactly that f is an injection from R mod E to R. So you cannot expect to prove this without. So how do we get rich from that? Well, it's a bit convoluted, but in modern finance, anything is possible. So you borrow size of real amount of money, or maybe you're rich and you already have it. And then you put it in boxes in this way. And you sell the boxes. And these boxes, each contain actually countably many points. So you just sell each box for $1 and you sell a countable amount of money for $1. We'll be very happy to get it. So you set the boxes, and then you end up with R mod E much money, which is much more than the money here. This is like that. So I'm not saying it's a practical scheme. No, there was no promise made in the abstract. Maybe there's a more like Banach-Tarski way of getting something from nothing, but I haven't found it. So I don't know. This is the best I have. All right, so let's look at the proof of that. And actually, the equivalence relation in the classes and the set is very simple. So definition, I'm going to let x be the set of functions from z to 0, 1. So you can think of them as bit strings, but going both ends, infinite bit string, going both directions. So I don't know, an example would be 1, 0, 0, 1, 1, 1, going somewhere this way, but also on the other way. And I'm going to say that two functions are equivalent if they are the same at two shifts. So for fg in x, f is equivalent to g if and only if there exists k integer such that f of n equals g of n for every n. Right, so that's the definition. And well, okay, I told you it was R, but this set X has a bijection to the real. Just thinking of the reals as using the base 2 expansion, for example. So we'll show that X mod E has bigger size than X. This is just the size of the reals. In the sense I mentioned before. So what's the intuition? So what is X mod E? Well, basically so each of those strings have a 0th position. They have a center. And so by modding out with E, you forget the center of the string. You don't remember where the center was. And that's it. So that's why I think Michael Reliver called it how to get more things by forgetting something. Forget where the center is, and then you have more things suddenly. Okay. So let's get started. I think let's use the definition. That's it. So let's see the easy coding case. Let's show that there is an injection from X to X mod E. This doesn't use anything about the axiom of choice. So let's think about it for a second. What do I want to do? I want to get, given a string like this with a center, I want to map it to a string without center so that I can recover the string even though I forgot where the center was. So if I send a shifted string, it should send to a different place. So this is just some coding argument. So let's do that. So I will just give you a couple of definitions and then the coding will all become clear. So for a bit b, 0, 1, I'm going to define b bar to be 1, 1 if b is 1 and just 1 if b is 0. So I'm just using unary, using base 1 for base 2. And for a finite string, say is 0 to bn minus 1 bits, I'm gonna define s bar to be b0 bar, then a 0, then b1 bar, then a 0, b2 bar, so on, up to b0 and bn minus 1. Okay, so I'm just coding things so that each place in the string is separated by 0, and what information of the bit is coded only by once. And finally, and now I'm going to code f in this set, in X, the following way. F bar is going to be the following infinite sequence. It's going to be, so F bar is going to be in X, and it's going to consist of, okay, a bunch of zeros at the beginning. You don't really care. Let's say this is position 0. I start with 2 zeros. Then I code f of 0 using this technique. Then I write 2 zeros. Then I code f of -1, f of 0, f of 1 as a string. Then I continue. I code f of -2, f of 1, f of 0, f of 1, f of 2. And so I continue this way. And now I claim that if I mod this out by, then I'm going to define this function. So f from x to x mod b be defined by send little f to f bar equivalent plus f. So the idea is going to be, no matter how I shift this thing, I can still recover the original f from that. And you should convince yourself of that, because all I have to do, given a string like this, is to find 2 zeros somewhere. It doesn't matter how it's shifted, just find 2 zeros, and then start reading from left to right from there, and you will just recover. You might miss out on the beginning of the string, but it's redundantly encoded all along. So this is how you read it. So then after the injection. Intuitive is because it's so redundantly encoded that no matter how you shift it, there will still be, the information will still be there. All of the string will still be contained, uniformly distributed through all this F bar. Right. So that's it. So this is why it's information. And I haven't used anything about choice or anything. There's no nasty business. Excellent. So one direction is there. And now I want to do the other direction. So I want to show that there is no injection from x mod e to x. And remember, I'm assuming that all sets are measurables. This is where something is going to go wrong. I'm going to appeal to some facts about measurable sets that on a non-measurable set, really with the axiom of choice, but with assuming all sets are measurable, it would be measurable. All right. So I have to say a little bit about ergodicity. So definition. If I take a subset of X, I will say it's a shift invariant. If, well, remember, these are just bit strings with going all the way to the left and to the right. So if any shift is also contained X, so F in A and F equivalent to G implies that this is. And then there is a fact. I'll explain more, but I'll just take it as a fact. Fact of measure theory, really, that if you look at the measure of A, it's going to be either 0 or 1 if it's shift invariant. So for any shift invariant A, U of A is zero. So by what measure am I taking? I'm taking the probability measure I can build by the product construction. So you don't have to know all of measure theory to know. I mean, you don't have to be able to construct the measure to understand this statement. Basically, I'm looking at probabilities casually, and so for example, I can look at any probability question on my strings. So the probability that a random string uniformly chosen at random has 0. This probability, where you can compute it directly, is going to be 1. Because the only string that doesn't have it is just a string of 1s, and there are not too many strings. There's just one string, it has measure of 0. But this fact tells you that if you take a shift invariant event, so I should say probability that a random string has a 0 at the 0th position, that's not shift invariant because, well, it depends on the 0th position. So this probability actually is 1/2 if you calculate it, but it doesn't contradict this result. This is only about shift invariance. All right, so basically it's saying if you take any probability question about a random string in X, uniformly distributed at random, and the question doesn't depend on how X is shifted, the result will be either 0 or 1. So that's a fact of ergodic measure theory, I guess. You can look at the construction of the product measure and do it. I mean, I'm not sure exactly how you do it actually, but it looks reasonable. I think you go through the product measure and it has this finitely property, and so you can yes. Anyway, I just take this as a granted. And you might wonder if this doesn't use the axiom of choice, and this might use a little bit, but not enough. I mean, this uses just DC or this weak version of choice that we can assume. So this is fine. So I'm going to use this fact. Yeah.
That just looks like the form of the Kolmogorov 0,
Yeah.
1.
It's the Kolmogorov 0, 1, yeah. So it's cool. Okay, so I know any probability question can be answered by either 0 or 1 if it's invariant. So at that point, I think I'm ready to start actually to show that there is no injection. From, where did it go? X might be X. So all these proofs, I mean, maybe you've seen, probably you've seen Cantor's proof that the reals are not countable. So this basically, Cantor's proof is showing that there is no injection from the reals in a natural number. And the way it goes is assume for a contradiction it fails, and then do some kind of diagonalization. And the proof would be similar. And I'll use ergodicity to do my diagonalization. So assume is false. So assume for the sake of contradiction, there is sigma an injection. Good. So if you take the sigma, and now you let S be a random string. I'm going to ask some questions about X. And I'm going to look at alpha. That's the probability that if I take the equivalence class of S and I send it over to x, and I look at the nth position, this is equal to 1. So basically I take a random string, I forget its center, then I use my injection sigma to send it back to a string with center, and I look at the nth position. So that's prop that the nth position of sigma of S with center forgotten. Is 1. So that's n is any integer.
How do you know this event is in the sigma algebra?
Well, there's no sigma algebra. All sets are measurable.
Okay.
So that's where
So the sigma algebra
that's
is
where
the
analysis
hardest
would be annoyed. Yeah, it's much easier to develop a measure theory if all sets are measurable. Right? So this event is in the sigma algebra because the sigma algebra contains everything. But you're right. I mean, this is where. And also you can check its shift invariant because this equivalence class does not depend obviously on the shift. And so by ergodicity, alpha n is a number that's either 0 or 1. It cannot be anything else. Okay, so I have this alpha n, and they actually form a string themselves. So I'm going to look at where my injection sends the string. That's where diagonalization is going to happen. So so I'm going to let the bad string. So I'm going to define a bad string in S. Maybe I should call it F bad, because it's not a regular one this time. And so F bad is going to be alpha. And it's an element of X because again, by ergodicity, every alpha n is a bit. Okay. Now I'm going to compute the probability that S is equal to F bad. So I'm going to compute the probability that a random string is equal to a specific string. So by just the usual measure theoretic argument, I mean, there's only one string like this, and so this must be 0.
Wait, doesn't F bad depend on your choice of S?
S is random, it's a random variable. So I'm not.
Yeah, but now you're looking at the probability of S equaling something. Like F.
So F bad is a constant now? I've defined it. So you could look at the
Oh,
probability
I
of
see,
S being
yes.
equal to the 0 string.
Okay.
And that would be 0 for exactly the same reason. I'm just saying it doesn't matter if it's a 0 string or any specific string. Right, so this one is an RB. This one is constant. Right. So this is 0 on the one hand. Then I'm going to argue it's 1 actually because of the weird way that we have defined as bad. So let's look. Let's fix some particular n, and let's look at the probability that they are equal at position n. Probability that S of n equals F bad. Okay, so let's see. There are two cases. We have to look at what happens if alpha n is 1 and what happens if alpha n is 0. If alpha n is 1, I want to argue that this is 1 no matter what. But let's see, if alpha n is 1, this means that the probability that I send this string and the result here is 1. Oh, I'm sorry, I think it's not what I want.
You want to
No, I think
sigma,
it's
sigma
fine.
first, right?
I think I want sigma like this. I think that's what I want. Yeah. This is 0, and I should say this is 0 by injectivity. This is what I'm using injectivity. Because otherwise I could have a map sigma that just sends everything as bad, and this probability would be 1. But I know it's injective, so if I pull this event back to x, I will just get the event that s is equal to 0. Okay, so this is what I want to do. So if alpha n is 1, probability, this is sigma again. The notation becomes less. But yeah, if alpha is 1, this is right, because this is a probability that I'll just write it very carefully. But by that point, you should begin to see it's equals to 1. This is if alpha is 1, just by substituting. But no, this thing is just alpha n. And it's just, and if alpha n is 0, well, this is the probability that this string is 0. But the probability that this string is 0 is 1 minus the probability that this string is 1. So it's 1 minus alpha n. So it's just 1. So in conclusion, this is 1. So for a fixed n, the probability that where I send my string evaluated at n is equal to f bar of n is 1. And so then by additivity of probabilities, I should get that the whole probability is 1. So by, I think it's called sigma additivity. Probability that sigma is equals f bar. Right, they're all 1 at each position. They're only countably many positions. So, well, on the one hand, I have some probability that is 1, and then on the other, I have the same probability that is 0. And that's a contradiction. So, of course, I mean, if you think about it in terms of what happens if you assume the axiom of choice, well, the mistake was pretty clear. I mean, all those events are very weird. They're not going to be measurable. But here all sets are measurable, so it's all fine. So it does show, though, that there is no measurable injection from x body to x. There is no nicely definable injection. So that's something that this shows in general. So that's sort of the beginning of a theory of definable cardinalities, where instead of looking at general injections, you look at injections that have some niceness conditions. So for example, being Borel or being measurable. But for our purpose, this proves the theorem.
So from the proof, can I claim that whenever you have a function from the equivalence class to x, then the values concentrates on a certain...
Yeah, I think you should be able to conclude that. Because, yeah, you
because
should be able to conclude
concentrates
that.
on f bat, right? F bat is like a majority vote.
Yeah, so this function cannot be an injection. So this means that this probability has to be 1. So yeah, this is a... Yeah, there are ways to turn around this to get very interesting results. But for the purpose of getting rich, this suffices. Okay, so what does it all mean? this is a short talk, so I'll just end with some remarks. So what does this all mean? I don't know. So I've kind of shown you that assuming choice, you have some very weird things happening, and assuming choice fails, you also have some very weird things happening. So to me, it just says that infinity is counterintuitive, like it's very hard to get a grasp on it. I should say though that there is still one opening here. I assumed all sets were measurable, so it's not exactly the negation of the axiom of choice. So maybe there is still some universe where not all sets are measurable, but there are not too many paradoxes. I don't know. Also, like I said before, I haven't found any compact paradox like the Banach-Tarski one. This one has to look at the reals and equivalence classes, like at very uncountable objects, whereas, okay, the ball is an uncountable object technically, but it still has measure 1, so it's kind of a very finitely paradox, the Banach-Tarski paradox is. I don't know where to find such an example in that case. Yeah, I don't know actually if the Banach-Tarski paradox works, just assuming the existence of an unmeasurable set, but I don't think so. So, yeah, that concludes the talk. Any questions? Yeah.
So, was the only thing that went wrong with this that like you didn't have to check that a certain set was measurable because it's automatically measurable?
Yeah.
And where this fails classically is you need to check it's measurable and you can't.
Yeah.
Okay.
So classically,
It's pretty neat.
yeah. So the only mistake here, if you assume choice, is I don't know where the event went wrong. I think already the definition of F bad is pretty based on non-measurable sets, but it's showing that yeah, you can have an injection, but it's not a measurable injection, so you don't know that the image is measurable in any sense. This is the only thing that went wrong. All the rest is fine. So you can also, like I said, get many conclusions just from that. So yeah, I don't know anything about this. Maybe even Andy knows more about it than I do. But there is this nice theory of Borel cardinalities. So you can look at cardinalities. The theory of cardinalities, if you restrict your injections to be Borel, very nicely definable. So what you end up having is a picture like, okay, the finite things finite. But in that case, you have the continuum hypothesis. So you have the size of the real is the next thing after a if not, in some sense. And then you have the size of this equivalence relation. That's the next thing, there's nothing there. And then it becomes very, very complicated. It's not even linearly ordered, it's a tree. I don't think people really understand what's going on. I mean, they try to prove non-structural results, actually. You can find any suborder in some high enough initial segment of this tree. But I find it pretty neat that there is like a Borel continuum hypothesis. So there is no RF1, RF2, or anything like this. It just goes directly to the reals in that case. So yeah, that's what happens there. Right.
Any other comments? Alright, let's thank Sebastien.
In fact, like, so one way of phrasing a